Non-conservative nature of induced electric field. So we have already seen that induced electric field lines form closed loops. So let us take this path for example. So it is a closed path and the electric field lines are counterclockwise on this whole path. So if we take a small charge q and we slowly carry this small charge q on this path and bring it back to its starting position. So what will be the work done by electric field? So small work done to take this to a distance dl is dl into qe, and for the total path the total work done will be integral of qe into dl. So this is the line integral which we are doing on the path. Now here you can see that this is not equal to 0. In this particular case it is greater than 0, because on the whole path everywhere dl and e are in the same direction. So dl dot qe is going to be positive for each dl on the entire path. So work done in bringing the charge back to the original position is not 0. So non-zero work for a closed path means induced electric field is non-conservative in nature. This is in contrast with electric field due to static charges. That was conservative, but induced electric field is non-conservative. We can, however, for a given path, calculate the potential difference across 2 points. Suppose you take one point here and you take another point here. And if you do qe dot dl for this path from here to here, you will get some value. And whatever that value is, that is the potential difference between these 2 points, if the charge is carried on this path. Now again, this is non-conservative in nature. So non-conservative nature means that if the path is different, the potential difference will be different too. So if we carry this path, so this charge along this circular path to, let's say, this point, and I take it from some other path to the same point, then work done in both the paths will be different, because it is a non-conservative field. But on any given path, I can calculate what will be the potential difference between the 2 points. Let us understand this more clearly with an example. So in this example, inside a solenoid, magnetic field varies as B is equal to Ct. So this is time varying magnetic field where C is a constant. Now 2 conductors are placed inside it with nearly touching ends. Find potential difference across PQ for each of them. So these are the 2 conductors. One is straight line, along the straight line, and another is semicircular arc. So we need to find the potential difference at the end of each of these 2 conductors. Now if this were a conservative field, then the potential difference would be same. Doesn't matter you go from this path or you go straight. But here let's see what will be the 2 values for the potential difference. So for A path, semicircular path, let's do the B path part first, that is easier. So we have to go from P to Q. Now the field lines, because of the solenoid, will be circular in nature. We have already seen that. So if you go along the diameter, then at every point field lines are perpendicular to the conductor. Because the field lines are circular, so they will cut the diameter at 90 degrees. So if you go across this conductor, your E dot dl at any point is 0, which means potential at Q is equal to potential at P. Now if we go between the same 2 points P and Q, but this time in a circular path, Now on a circular path, the field line will also be circular because it's inside of a solenoid. And this value of E we have already proved before. For a solenoid it is x by 2 times dB by dt. So E becomes x by 2 times dB by dt of Ct will be C. So this becomes Cx by 2. So EMF is E dot dl and its integral along the path PQ. So E is Cx by 2 times dl for the path PQ. Now for the path PQ, Cx and 2 are constant, so we'll take it out. If we do integral of dl when we go from Q to P, that will be the pi into x, length of this arc. So VQ minus VP becomes pi C x square by 2. So you can see that depending on the different paths, different values we are getting. So different EMFs across same set of points because the path chosen is different. But again, we can define potential difference between P and Q if we give the path or if we put a conductor in a particular way. Then we can say that VQ minus VP is pi Cx square by 2. And if you actually connect these two ends with a wire, then the current will flow through it and its value will be pi Cx square by 2 divided by resistance of the whole path.